In this section, we're going to be looking at differential equations and growth and decay problems. So the first thing we want to talk about is differential equations. So if you want to try to solve y prime equals something like 3x over y, what you're trying to do is find an equation for y that does not involve the derivative. So I'm going to start off by rewriting y prime as dy over dx. And I'm going to put that in the differential form, dy equals 3x over y times dx. And then I'm going to actually multiply both sides by the y in order to clear the fraction and to get all of the same variable on each side of the equation. So notice that on the left I now have y's and on the right I now have x's. So what I'm going to do now is I'm going to take the integral of both sides. And on the left, I get y squared over 2. I'm only going to use one constant because I don't really need to write it twice. If it's on the left or the right side of the equation, it doesn't really matter. This one will be 3/2 x squared plus c. And typically when you can't solve for y, the thing that you want to do is actually solve for the constant. So I would subtract, and I would get y squared over 2 minus 3/2 x squared equals c. And that would be my answer. Just to do a couple more of these, if I wanted to solve, for example, y prime equals 12, this one's a pretty simple one. I'd have dy over dx equals 12. Again, I'd write that in differential form. And I'd take the integral of both sides. The integral of with respect to y is just y. The integral of 12 with respect to x is going to be 12x plus c. And since I can solve for y, I'll leave it there. Another one, you might be asked to solve dy over dx equals something like xy. So I would start off by writing this as dy equals xy dx, and then I would divide by y. So that gives me 1 over y dy equals x dx, and then I'll take the integral of both sides. So this would be the natural log of the absolute value of y. This would be x squared over 2 plus c. Now, some people would leave it there. If you can get rid of the natural log, more better. So I would take e and raise it to both sides. So e to the natural log of the absolute value of y is just the absolute value of y. This one's kind of interesting because I've got e raised to a sum, so I could write that as e to the x squared over 2 times e to the c, and instead of c, let's call it c star. Because e to the c star is just a constant. So this is a constant, and we're going to call it c, and I'm going to put it out front. So I get c e to the x squared over 2, and that would be my answer. And you can leave the absolute value bars on there because we don't know for sure what c would be, but in this case it would force it to be positive. So we'll leave it like that. You may have something really simple like y prime equals 2x plus 4. So this would be dy over dx equals 2x plus 4. You would bring the dx over, take the integral of both sides. That gives me y equals x squared plus 4x plus c. And that's all you can do there. You may actually have some like this where y prime is equal to y. So dy over dx equals y, so I would write that as dy equals y dx. And then just to make life a little bit easier, I'm going to divide by y, so I get 1 over y dy equals dx. And then I'll take the integral of both sides. So again, this is going to give me the natural log of the absolute value of y, just like this one over here. This is just going to give me x plus some c star. So I would take e and raise it to both sides. So I would get the absolute value of y equals e to the x times e to that c star. And the absolute value of y is equal to c e to the x. And typically we don't leave the absolute values on there. We just assume that c is going to be positive. So this is the solution to this equation. Now that last problem we did where we had y prime equals y or dy over dx equals y, This is a version of this particular equation where dy over dt is equal to k times y. So this is the rate of change of y is proportional to y because it's a constant times y. And the general solution of this is always going to take one of these forms, c e raised to some power. And in fact, in this case, it's always going to be c e to the kt. So c is the initial value of y, and k is the proportionality constant. Exponential growth is going to occur when k is greater than 0, and exponential decay is going to occur when k is less than 0. In 5.5, we looked at an example with half-life. Half-life is a specialized version of exponential decay. You can actually derive that formula using this process and the natural exponential base rules. So, as an application, it says as an example, it says the rate of change of n is proportional to n. So that's just saying we're using this model. When t equals 0, n equals 250, and when t equals 1, n equals 400. So it wants to know what is the value of n when t is equal to 4. So the rate of change being proportional, this is saying that dn over dt is equal to some k times n, which means that n is equal to c e to the kt if you were to solve that. So when t equals 0, n equals 250. So this is the initial population, but you can see that by plugging in t equals 0. So you get 250 equals c times 1, or c equals 250. So that creates the equation n equals 250 e to the kt. Then we'll use the second piece of data, t equals 1, n equals 400, to find rk. So in this case, I would have 400 equals 250 e to the k times 1. I'm working from this version of it. So 400 equals 250 e to the k, so I'm going to divide by 250. So 400 over 250 is 1.6 equals e to the k, and then I'm going to take the natural log of both sides. So I get that k equals the natural log of 1.6. So n equals 250 times e to the natural log of 1.6t. If you want to leave it that way, that's fine. Or you could actually, raise the power to a power here and make this 250 times 1.6 to the t. There's nothing wrong with that as well. So the problem said, what is the value of n when t equals 4? So we're actually trying to find when t equals 4, what is n, using this version. So n would be 250 times 1.6 to the 4th power. Which gives me 1638.4. So that would be my answer. And like I said earlier, radioactive decay is measured in terms of half-life, which is the amount of time it takes for half of a sample to decay. And this rate is proportional to the amount that's present at whatever time you start. So this is saying that if x equals the amount you have, then dx over dt is equal to k times x, which tells me that x is equal to some c e to the kt. So at t equals 0, in this problem, x is equal to x of 0, so we don't know whatever that amount is. That's the initial amount. So that's going to give me the fact that x is equal to x of 0 e to the kt. And then I know that when t is 1599, x is going to be half of the initial amount. So that means I have 1/2 x of 0 equals x of 0 times e to the k times 1599, because that's the half-life. And I can cancel the x of 0, so I get 1/2 equals e to the 1599k, and I'm going to take the natural log of both sides. So natural log of 1/2 equals 1599k, and k would be the natural log of 1/2 divided by 1599. So that means that x would be x sub 0 times e to the natural log of 1/2 divided by 1599 times t, or I could actually write kind of parentheses around this if I wanted to, or I could even make that e to the natural log of 1/2 raised to the t over 1599, and the natural log of 1/2 is 1/2. So you can see that this is the half-life formula we talked about in the last section. So this says that after 200 years, x would be equal to x sub 0 times 1/2 to the 200 divided by 1599, which is x sub 0 times this lovely decimal point 91695, so on and so forth. So this says that after 200 years, approximately, this looks like 91.7% of the original sample will remain. And for this problem, we weren't given an original amount, so it's just asking for a percentage, so that's what we're looking for. And you can see that that's 0.917 times the original amount, x sub 0.